Thank you for having me here in the Munich NLP group. Really looking forward to introduce you to like the next generation of semantic search. So I work as director of machine learning or principal scientist at cohereai. Before that, I've been doing my PhD in Darmstadt at the UKP Lab and doing my postdoc. Then I've been research scientist at huggingface, and now I'm principal scientist at Cohere, working on the next generation of semantic search. So Cohere, if you're not familiar with our company, we bring the next generation of powerful NLP to developers and businesses. So we have world-class NLP models for text generation, classification, and embeddings, up to like 100 billions of parameters. And you're able to adapt these to your data sets, and it's easy for you to use as a pay-as-you-go API, so no commitments you have to do. And they are all speed optimized so that you get like a really nice and quick experience and can use these massive language models for every use case you're interested in. So for today's talk, I would like to talk about neural search, sometimes also called semantic search. And there has been, if you follow the scientific community and companies and startups, there has been quite a lot of hype about it. And to show you that neural search is really, really interesting, really good, I have here a real example on the Wikipedia, on the simple English version of Wikipedia, which has about 170,000 documents. And if you ask a really simple question like, what's the capital of United States? And you search in it with lexical search using Elasticsearch and BM25, the first three entries you find is on, or the first entry is on capital punishment, because it contains the word capital and it contains the words United States. So here you have like a high overlap of capital in United States. Second entry is on Ohio, because it's a state in the United States and it has a capital. And the third entry is on Nevada, because it's also a state in the United States and it has a capital. From a user perspective, lexical search is completely useless, and I don't know, every search tool which is not Google or maybe Bing is really frustrating to use. So if you still use Outlook or Thunderbird or Notion or Microsoft Explorer, the search is really, really frustrating because it never finds the relevant documents you're looking for. In contrast, when you use search, an out-of-the-box neural search approach, and you type in the same search query, the first entry is on Washington, D.C., so that's the perfect answer. Second entry is on capital city, so what's the capital city? And the third entry is on the United States Capitol, because maybe you misspelled the word capital and you were looking for the information, what's the capital of the United States. You can also put this into numbers, so it's not only like a cherry-picked example, but here we have a quite old benchmark from 2004. So in 2004, the NIST created a benchmark to evaluate information retrieval systems. And the solid black line is the best system in 2004. And as you see in 2018, none of these systems were better than the best systems from 2004. So 14 years, no, there have been like no progress in information retrieval, and even longer than that. And then in 2019, the BERT paper was published, and people used it in 2019 for information retrieval. And we saw for the first time some improvement, or nice improvement, over the old 2004 system. And then in 2020, it improved further, and same trend follows in 21 and 22. So that we have now extremely good search system thanks to neural networks. Also, industry quickly catched up with it. So not only academic benchmarks found that neural search systems perform extremely well. So Google in 2019, they rolled out the transformer networks into the Google search application. And they say this is the biggest leap forward in the past 5 years, one of the biggest leaps forward in the history of search. So even such that search worked extremely good in 2019 for Google, adding neural networks, BERT networks to them improved it significantly. Same impression came from Bing. They say they launched it in April 2019, and they say it's the largest quality improvement over the past year. So they see significantly improve results thanks to neural networks. There are different ways how you can use neural networks to do search. Today I want to focus on semantic search. So when people talk about semantic search, they often mean Bi-Encoders, also often mean dense vector spaces. And you have a lot of companies focusing on vector databases. So a lot of startups try to address these markets, how you can work in these vector spaces and find relevant entries in the vector spaces. And also some really cool companies from Germany are taking place in this. Not sure if there are companies from Munich also, but there's like a lot of startups and opportunities to work on vector spaces, on vector databases, on models, and so on. So one really common approach in industry are so-called Bi-Encoders, which work on vector spaces. So you take all the documents you have, for example, all Wikipedia documents, or all Slack messages, or all Twitter messages. You encode them in the vector space with some neural network model, and then a new query comes in. You also map it to the vector space, and you check what are the closest point in the vector space, and then you say, okay, these points are relevant documents. And how does it look like from the model side? So you have some transformer model, for example, the BERT model. You encode the query, you encode the document. You get as an output the contextualized word embeddings for all the query tokens and all the document tokens, where you then run pooling on it to get the average. You run average pooling to get a fixed size vector. And then you can compare the vector for the query and compare the vector for the document, for example, using with cosine similarity to see how close is the query to the document in the vector space. And if you have a good model, this corresponds to that the document is relevant for the given query, for the given search query. What's nice is that it's not limited to only text search, can go across modalities. So for example, you have like a lot of images embedded in a vector space, and then you search for 2 dogs in the snow, and then it finds that this image is close to the search query, and you can retrieve it for the user without needing to transcribe what you see in the image and to search on the image description, but you can really search on the pixels of the image. It's also not limited to a single language, so you operate in these vector spaces, so you can map text of different languages to the same point. So independent if you search in English or in German, it's roughly mapped to the same point in the vector space. And then when you search for 2 Hunde im Schnee, you find this cute image of the 2 dogs in the snow, and you can retrieve it to the user. So dense Bi-Encoders, they provide a lot of benefits to it. First, they can overcome the lexical gap. So in lexical search, when you search for USA, it will not find any documents on United States. But embedding models, they don't, because they don't work on a word level, but on these vector spaces, they don't care about if you say US, USA, or United States, it will find these documents. Can also respect the word order. So when you do lexical search and you want to get information, how do I get a visa as a German to Canada, or how do I get a visa in Canada to Germany? They will find the same queries because they cannot respect the word order. But dense Bi-Encoder models, they know, okay, these 2 search queries are different, requiring to match to different documents. And finally, they also know about related terms. So maybe you search for how can I compute the Spearman correlation in NumPy, but there's no such function in NumPy, but in fact, there's a function to compute Spearman correlation in SciPy. And the model knows that NumPy and SciPy are really similar libraries, which you can easily use interchangeably. So it recommends you an entry how you can compute Spearman correlation in SciPy instead of finding a document how to compute Spearman correlation in, for example, some Java library. So one challenge is how you can find like these closest point in the vector space. For us as a human, we think it's easy. So we see here's the query, and then we just look at it and say, okay, these are the points that are closest in the document, which we want to return as search results. However, for a computer, they cannot look at it. So instead, you have to find like smart ways how you can quickly identify that these are the closest point in the vector space, where a lot of companies are working on this problem, which you know them as vector databases. So one option, which is not too bad, is to use brute force. So you have some search query, and then you check for all the documents in the vector space, the distance, and then you sort them by the shortest distance. So you say, okay, you measure the distance for every point, and then you find the top 10 closest points and you return them. Obviously, the issue is that the query time grows linear with the vectors. So if you increase the number of vectors to like 1 million, the query time increases linearly. So I would say it's only suitable if you have like 10,000 to 100,000 vectors. There the query time is like small enough and doable, but above that, it's often like too slow. And what you then need to do is so-called approximate nearest neighbor methods. There's like a whole body of literature on approximate nearest neighbor methods. Here I want to just give a glimpse on like two common approaches. The first approach is IVF, where you take the vector space and first you run the vector space in a k-means clustering. So you cluster the vector space in 10, 100, thousands of cells. And then when the query comes in the first step, you check what are the closest cells. So if the query is here, you say, okay, here I have like the different centroids of the cells. And then you say, okay, here, these are the 8 cells that are the closest to the query. And then in these cells, you search for close points using brute force. So here, instead of having to do brute force over all the points, you just do brute force in this small subset of the vectors. Another approach which is really popular is HNSW, which is Hierarchical Navigational Small World. It depends on a multi-layer graph. So in the first layer, you have only a few points with really large distances between these points. And then the query comes in, which we call the start data point, and you find in the topmost layer what's the closest point. Once you found this point, you go to the next layer, which is denser, where you have more points in the vector space, and you have pre-computed the closest neighbors to it. So you know for this point, the closest neighbors this and this. So you check, okay, which of these two neighbors are the closest to the starting point. Once you found the closest point in this second layer, you go to the next layer, which is even denser, contains even more points, and you continue to look, okay, what's like the closest points in this vector space. So in the top layer, you make like big jumps to get closer to the nearest neighbors, and then once the more you go down the layers, the smaller the jumps and the more dense the vector space becomes until you find the nearest neighbor. There's like big trade-off between these methods. So there's a big trade-off. How long does it take to create these indices? How fast is it to find the nearest neighbor using different techniques? How much memory does it require? How big is the storage size? And then depending on what you need, do you need like a fast approach and you're willing to pay premium? You can use the one approach, for example, HNSW. It's extremely fast, but also really expensive. IVF in comparison is cheaper, but not as good. And then you have to find for your specific application, what's the trade-off you want to do between like cost and quality. And then you can optimize for the one or the other approach. So today I want to talk a bit more on how to train these representation models, because the representation models, these are really the key component to find relevant documents, and that's where we at Cohere are focusing on. So we focus on training the best representation models so that it doesn't matter how complex your query is, when you type it in, you get the perfect response for you. And one simple approach is to use so-called multiple negative ranking loss. So this requires that you have positive pairs like A1, P1, A2, P2, A3, P3. And what the pairs are depends on your scenario. So this can be, for example, a query and the answer passage. It can be a question and a duplicate question, what can be the title of a scientific paper, and this paper cites another paper title, and you can create like a pair like this. And what you want is that this pair is like close in the vector space. So A1 and P1 should be close in the vector space. And then all the other points, so A1 to P2 to P3, P3, P4, P5, they should all be distant in the vector space. So you train it such that A1 and P1 gets pulled together in the vector space, and all the other points are pushed away in the vector space. And if you train on like query answer passages, what you get is that the query and the relevant document, the answer document, are close in the vector space, and all the other answers are distant in the vector space. And this allows you to search then in the vector space. To give a more intuitive explanation, so for example, you have a question, how many people live in Berlin? And then you have like 3 different answers. P1 is the correct answer to A1, so around 3.5 million people live in Berlin. And then you have 2 different answers. Washington, D.C. is the capital of the US, and the 21 Olympics are held in Japan. And you can see it kind of like a multiple choice test. So you have this question given, and you want to know from the model which one is the correct answer. So what you do is you compute the text embeddings, and then you compute the cosine similarities. So for example, between A1 and P1, you have a 0.5 similarity, A1 and P2 0.3, and A1 and P3 a 0.1 similarity. And then you say, okay, this is my prediction. So for A1, I have the prediction of 0.5, 0.3, and 0.1. And you know from the training setup that the correct answer is P1. So you want a really high similarity for the first combination, A1, P1. And you want a really low 0 similarity between all the other answers. And then you can just use cross-entropy loss. So it's like a normal classification task. In this case, you have 3 labels. The correct label is label 0 or label 1. And you can do backpropagation and train the embedding model using this loss. There's a lot more theory how you can improve training, how you can create better batches, how your data has to look like, how you can do data cleaning. I will not be able to talk on this today. If you're interested, you can go on my website, so nils-reimers.de. There is a section on research talks where I give like an hour-long explanation how you can tune these models to get like to work better and get really state-of-the-art performance for search or other applications where you use an embedding model. Today I want to talk about one section which people often do not talk a lot about, because if you read research papers, every research paper says, okay, semantic search is amazing. If you read the marketing and PR from companies, vector databases, they of course also say semantic search is amazing because they want to convince you that you switch from lexical search to semantic search. But today I want to talk a bit more about shortcomings, so scenarios where semantic search doesn't work. It works for a certain number of applications, but there are also applications where it doesn't work well. So fields of issues. So I want to talk about 4 different issues. The first is keyword search, then multiple topics per text, unknown words, which is connected also to domain shift and data drift, and long documents, and then explain why the current approaches perform really poorly on these applications, and what could the next generation of search model look like to overcome the issue. So semantic search is good if you have like complex questions and want to find an answer. But sometimes you just want to do keyword search. So you want to search for a specific phone number and want to find this specific phone number. Or you search for a certain ISBN code, or you search for a specific error code you got from Windows, or you search for a really specific quote. And semantic search doesn't work well. So if you enter like phone number in it, it will not necessarily find documents with that phone number, but might find some other documents. And this is like kind of like bad user experience. So if you say, okay, this is like really simple search query, I have this one phone number and I want to find this one document containing this phone number. So why does it not work? But the solution is not too complex. So what you often do is you combine keyword and semantic search. So if the search query is more complex, you can run semantic search. If you just search for a phone number or some error code, you do keyword search. So this is solvable. More interesting challenge is if when you have multiple topics per text. So for example, you have a text, bananas are the most sold fruit, which you map in the vector space up here. And then you have a text, Facebook was founded by Mark Zuckerberg, which you embed into the vector space down here. And then someone writes like a crazy text like bananas are the most sold fruit. Facebook was founded by Mark Zuckerberg. It's totally valid to write a text like this, and you pass this to your embedding model. And the question is like, where should you embed this in the vector space? Should you embed it somewhere in between? Should you embed it like up here, down here, somewhere completely different angle in the vector space? And this causes many issues with these approaches. So probably you're familiar with word embeddings, and you can then visualize them nicely like in 2D, where you have like some things in your house like kitchen, bathroom, table, toilet up here, and here you have like things you can find in your garage like tools, drill, battery, saw. And the issue is like if now someone combines like two things, two vectors, like two topics in a single input, for example color and charger. If you look in the vector space and you put the average, you end up at kit. And you would ask like, okay, why is the average, or why is the combination close to kit? What's the connection there? And this is actually a real issue. So if you take a state-of-the-art model and you encode like 3 topics in it, bananas are the most sold fruit, Facebook was founded by Mark Zuckerberg, my favorite game is Counter-Strike, and you check what are matching questions. And typically, if you have a matching question, you get a really high similarity, close to 1. And here, some questions that have like a high similarity or that are kind of also the closest to it. So for example, who are Facebook's biggest competitors? Yes, the text talks about Facebook, but it's not talking about competitors. It asks like, what's the best board game ever? What are the best agent snacks you can buy on Amazon? And then only with like a really small cosine similarity of 0.44, it has similarity to who founded Facebook. So if I search for who founded Facebook, this would be, if this is like the only answer, the only text in my collection, I would say, yeah, it's good. I mean, it contains the information who founded Facebook. So why not retrieve it to it? So the ugly truth about semantic search is that it works best with like 1 topic per text and vector. So you could think about like, okay, just make sure that every text has only 1 topic, but this is an extremely challenging problem. So how can you check if a text has like multiple topics? When does it start to be like 2 topics? So if I talk about like Mark Zuckerberg founded Facebook, and then I talk about his college career, is it like one topic or is it 2 topics? So it's like really, really complicated to say when does like another topic start. Second issue is the challenge of unknown words. So all language evolves, new company names, new products, new concepts are created constantly. And if you take this new word and you embed it into a dense vector space, so Big Bird Pegasus is some transformer architecture for long documents, it has to find the right spot in the vector space without having ever seen this word. And if you check this in a real example and you encode it, the model thinks that this Big Bird Pegasus, which is the name for deep learning architectures to encode long documents with transformers, is connected to Big Boss, Big Data, and Big Ass. And the issue is that if you search for it, you get like this wrong mapping. So maybe the document talks about, so you search for Big Bird Pegasus, and instead you find like some documents talking about big data or big boss or big ass. So how do Bi-Encoders handle these unknown words? So first you can differentiate if it has seen the words during pre-training or during fine-tuning, but in general they handle these words really badly. And our language constantly evolves. So we have Big Bird Pegasus, a new transformer architecture. We have Clex Chain, which is a new cryptocurrency. We have Forward, which is some startup from Israel. And we have this error code, which is connected to an issue in the Windows activation. But if you just look at the surface form, so if you do not know it and I give you like this token, you would have no idea what is the meaning of it. And somehow we ask the model to infer the meaning, even such as like an impossible task to do this. Another big challenge are synonyms and related terms. So BERT was trained in 2018 for COVID-19. So it has like no idea that coronavirus, COVID-19 and SARS-CoV-2 is connected. Also synonyms, acronyms are a really big challenge. So if you ask like which vision transformer model is the best, and then the model does not know that VIT is a name for vision transformer for a specific type of transformer architecture, so it cannot make the connection between vision transformer and VIT. So these are like big challenges, unsolved challenges. We wanted to study this a bit more, so in 21 we created BEER, benchmarking IR, which targets zero-shot information retrieval. So how good do these models perform if you use them for unknown domains where it has not seen the data? And we collected a lot of data sets on different tasks, on different domains with different complexity. And we checked how good are these semantic search Bi-Encoders versus lexical search. So before that, everyone said, okay, semantic search is extremely good, and they showed it like in domain. So they had training data for it and then showed, okay, if you have training data for it, it works extremely good and much better than lexical search. So you get an 18-point NDCG at 10 improvement, which is like a really massive improvement every user will instantly notice. But if you go to more specialized domain, more complex domain, for example, BioAsk is a data set from the biomedical domain with a lot of domain-specific words the model has never seen, you notice that the model actually performs worse than lexical search because it tries to infer the meaning for words it has not seen. And in fact, lexical search was better on 10 out of 18 datasets than the state-of-the-art semantic search method at that time. Second big challenge is that transformers cannot deal with real documents. So BERT network, they can only encode 512 word pieces, which are 300 words. Some transformer architectures can maybe stretch this to thousands, 2,000 words. But however, a lot of these Bi-Encoders, semantic search models, they only can encode 128 word pieces, roughly 100 words. But this is not what you have when you search. So if you have real documents, they can look like this. So this is the Johnson & Johnson 21 annual report, which has 140 pages. So your model can handle 100 words, but people come with 140-page reports. Or even worse, it can look like this on Amazon. So you have some product image, you have a titles, you have some ratings, so you have some price, you have some features like categories, some description, some Q&As, some reviews. And how do you encode this complexity into a model that can just work on 100 words and only on a single text? How can it notice that there's a difference between the title and someone writing some text in these 1,000 ratings when these 200 answers questions for the product? So now I talked a lot about the shortcomings. Now I want to give a brief glimpse how the next generation of semantic search algorithms could look like. So this is just a hypothesis, and we have to do like more research on how they will work and which properties they have. One approach I want to talk about is sparse embeddings, which encodes to like a sparse high-dimensional vector space. Second approach I want to talk about are multi-embedding approaches. So instead of embedding to a single point, it embeds to multiple points. And hybrid embeddings, it's a combination of sparse embeddings and dense embeddings. So sparse embeddings are a rather new method to search. And here you project the output of BERT to the BERT vocabulary size. So BERT has a tokenizer of 30,000 word pieces, and then you project the output, the query, to like a 30,000 dimensional vector, but most of the entries are left empty, so are zero. So if you encode something like how to learn Python, it will notice that Python is a really relevant word. The document should contain the word guide, because if I search for how to learn Python, a document that contains Python and guide is probably a good document. It should also contain the word learn or teach. So if it talks about this Python guide, with this Python guide you can learn Python, that's a really good entry. But what can happen is that sometimes some dimensions are hard to interpret. So if on the document, if it includes a curly bracket, so that's also a strong indicator that this document is relevant to how to learn Python, which does not really make sense. Challenge of sparse embeddings, it's a back-of-word approach, so no word, it cannot preserve the word order. So if you search for how to fly for a flight from London to Paris or a flight from Paris to London, cannot differentiate the word order. Nice property is with these approaches that multiple topics or multiple discourses are not a challenge with sparse vectors. So if you have like bananas are the most sold fruit, relevant terms are banana and bananas, Facebook, relevant terms are Facebook and Zuckerberg, and here relevant terms are game, encounter, and Stripe. And if you now concatenate these three entries as a single text, you get a vector that includes the information about bananas, a vector that includes the information about Facebook, and a vector that includes the information about game. So no important information is lost. So if I search for the founder of Facebook, I still get like a high score with this document because it contains Facebook, Zuckerberg, and founder. So I can search for any of these three topics and find the concatenated document. Also, they work nicer for unknown words. So if I have a word Big Bird Pegasus and I don't know what it is, I should not try to infer meaning. So what I should do is just do lexical search. So if I search for Big Bird Pegasus, I don't know what it means. I just find documents that contain the word Big Bird Pegasus. And sparse encoders, they do the same. So they split the query into word pieces. So it's split into Big Bird Pegasus. So any document containing these word pieces will be found. And then it also tries to infer some related terms like bird and birds or big and giant. So if I search for giant bird Pegasus, it will also find the Big Bird Pegasus document. So this is also really nice behavior of sparse embedding models. You could think that you can solve also long document encoder with sparse vectors, but this is sadly not possible. So for example, you have the search query, which university did Michelle Obama attend? And you have two documents. Document A is Michelle Obama graduated from Princeton. She is married to Barack. And the second one, Barack Obama graduated from Columbia. He is married to Michelle. So sparse vectors like split, they are a back-of-word approach, so they don't preserve the word order. So this is just like doc A and doc B are scrambled, and you cannot tell from the scrambled back-of-word approach if doc A or doc B is more relevant for the query because both contain the same words, so both could be relevant for the query. And the longer the document, the more relevant the word order. So if I have a single sentence like Barack Obama graduated from Columbia, it doesn't matter that I do not preserve the word order because there are not like really a lot of combinations how I can combine these individual words. However, if I have a really long document, I do not want to find a document where it talks Barack Obama in the beginning and then you have like some 1,000 words in between and then it talks about graduated and then 1,000 words in between and then Columbia, because it might be completely irrelevant to the question from which university did Barack Obama graduate from. You could think about that long document encoding, you could do it with dense vectors because it can preserve the word order. But as mentioned, it has issues when you encode multiple discourses, topics per document, and you have a compression problem. So if you have a dense vectors with 512 dimensions, each dimension is a float 16, so that's in total 1024 bytes. So if you take the annual report from Johnson & Johnson with 100 pages, you actually try to ask the model to compress it to 124 bytes. So that's roughly 200 words. So kind of you try to do the miracle and compress a 140-page document to 200 words. So a lot of information will be lost in this compression. So sadly, non-document encoding is not possible with dense vectors either. Interesting approach is multi-vector approach. So we have like these multiple topics in a single text. So you could think like, yeah, just split it across the topics. So the information on bananas goes here, the information on Facebook dates goes here, and the information on the favorite game goes here. But there the challenge is like, how do you detect like how many topics are there? So it becomes like really, really hard to decide, does this text contain like one topic, 2 topics, 10 topics? And do this really in an automated way is extremely challenging. And it also increases your vector space. So the more fine-grained you are on the topic level, the more vectors you get and the more expensive it will be to search in the vector space. So the current solution for long document encoding looks the following. So you take this 140-page report from the Johnson & Johnson annual report, you chunk it into paragraphs. So you either look like for blank lines in the text, or you take some 100 words windows, and then you take these paragraphs and you encode them individually. And then you perform retrieval on the paragraph level. So you don't check, if you do a search query, what were the quarterly earnings of Johnson & Johnson in Q4 21. You don't check it on a document level, but you try to find it on a paragraph level. And then you say, okay, I got this paragraph from the annual report of Johnson & Johnson. Challenge is here when you chunk the text that you lose context information. So you lose the information that, for example, you have a text, the first paragraph talks about Barack Obama and was born on August 4th. And then there's a new paragraph, he graduated from Columbia. So here, if you just encode the second paragraph, you does not know what he stands for. So you lose the context information, and then you're not able to know, okay, that he stands for Barack Obama and should be encoded respectively. Final interesting approach are hybrid embeddings. So dense embeddings, they're good to encode topics. They can preserve word order. They have issue when there's like multiple discourses, multiple topics per text and unknown words. And in contrast, sparse embeddings, they're good with multiple topics, unknown words, but they have issues with word order. So people started to combine them. So you encode for every text, get a dense embedding, and you also get a sparse embedding. And then you encode them, or you retrieve them with both methods, and you combine the search results. And this gives you really good, strong results, so nice improvement. However, the challenge right now is that you have like 2 indices to maintain. So you have a dense index and a sparse index, so that's twice the size to manage and to run. And it can also be, depending on the setup, a bit hard to maintain 2 different vector databases, one vector database for dense embedding and different solution for sparse embeddings. But vector database vendors are working on this so that you can encode them into a single index. And then this is like a really nice approach to overcome certain limitations. So conclusion. So current semantic search works really good if the test data is similar to the training data. So in the best case, you have training data for your specific search scenario. It works good when the documents are short, so on a paragraph level, and when you have a single discourse, single topic per text fragment, then semantic search works extremely well. However, in fact, often your data looks more noisy, more messy. So you have some really long documents or like multi-field documents, and it's like really unclear how to encode them and how to search good on these solutions. And right now, the current existent approaches are extremely hacky, where people hack together different things to get it working so that you can do semantic search in an e-commerce store, for example. And so my team at Cohere, we are doing research on foundation models. How can we search documents that are of any length? So you will be able to provide us like 10-page, 100-page, 10,000-page report that have multiple fields, like in an e-commerce store where you differentiate between title and body of any modality. So it can include images, video, audio, and without labeled data. So that's the way where I want to go forward to. Thanks so much for listening. Are there any questions?
Thank you so much.
So,
this was really interesting.
Yeah, happy to answer any questions in the chat.
I see a question in the chat. Yeah.
So what are my thoughts about cosine similarity versus inner product similarity? Okay, I can also start my camera. So what's my question about cosine similarity and inner product similarity compared to TF, IDF, and BM25? It seems that cosine similarity cares about the fraction of document tokens that are similar to the query, while inner similarity cares about the total number of document tokens that are similar to the query. While BM25, TF, IDF can do more complex logic. So in our beer paper, we compare systems trained and used with cosine similarity and systems trained and used with inner product. So for search, I would say inner product works better. So cosine similarity, they have a tendency to retrieve shorter documents, because the more topics, the longer the document is, the longer the paragraph is, the more topics you have, and the less or the more blurry the topics become. And inner product, they can encode it by creating a larger vector. So the individual dimensions become larger. And so if you search, you find like longer paragraphs. At the end, it depends on the specific search application. So do you prefer to retrieve shorter paragraphs, like a single sentence? Or do you prefer to retrieve longer text, like a paragraph? In most cases, people like to retrieve longer text, so they like to retrieve more like a paragraph on that topic than a single sentence on that topic. Are there any further questions?
I see someone typing in the chat.
You can just type into the chat. We will go through the questions sequentially.
Yeah, someone is typing right now, so let's see. Okay, a few people are typing, so I think a few questions are coming. So what's the...
So the question is, what's the best way for domain adaptation? And just post paper, which we recently did on that. So called GPL, Generative Pseudo-Labeling for Unsupervised Domain Adaptation. Basically, there are like two ways for domain adaptation. One is adaptive pre-training. So you take your target domain, you run mass language modeling on it, and then you can train on like some labeled data you have from a different domain. But there the challenge is that for every domain, you have to do training on your source data again. And with generative pseudo-labeling, it's the opposite. So you can take a trained model and adapt it to the specific domain. And the longer you adapt it, the more cycles you run, the better it gets adapted to the domain. How the approach works is a bit too complex to answer it here in like a minute. There are some talks on it where I present it also next week at the Open NLP meetup in Berlin. I am going to present it in more detail, but the idea is to combine different approaches. So it combines text generation approach with the cross encoder to train embedding approaches.
Thank you for the answer. I think a few more questions are coming. So a few people are typing right now.
Okay, there's a question. What is being tested regarding combination of dense and sparse embeddings at the moment? I do understand how having two different embeddings benefit the search in general, but can't wrap my head around a concrete way to mix them at the end. So right now what people do is they combine BM25 lexical search with dense embeddings. So in the most simple case, you use Elasticsearch and you hit the query to Elasticsearch to get like the top 10 results from Elasticsearch. And you do the same with the dense embedding. You take the query, you pass it through a transformer network to get a dense embedding, and you send it to like a dense vector database, and you get the top 10 results. And then you have like two results lists. There are different ways how you can combine it and different research on it. What works well is two ways is like either taking the ranking position. So you say, okay, this document was on position 1 and also on position 1 for both of these lists, so it should go to position 1. So you say, okay, I take for every document the score 1 over the position, and then you add it for both systems. Or you do an interpolation between the scores, so you normalize the score of BM25 and normalize the score for cosine similarity to a range between 0 and 1. And then you do a weighting, so you take 0.2 times the BM25 score plus 0.8 the cosine similarity score. And then this is like the final score where you can do the ranking on it. So there's a question. So you have a query, can I have mobile number? And there's a sentence, I need your mobile number for reference. Both query and sentence are close, but I need to extract only I need your mobile number from sentence based on query. I have done by using n-gram approach, and it's just computationally expensive. Just want to know any other approach to solve the problem. Not sure if I'm understanding correctly. I sadly do not understand it, so if you could clarify on the question, then I could maybe try to answer that.
Okay, so I think a clarification is coming.
So I'm not sure how to
Yes.
unmute.
Let me just.
So I'm sadly.
So you should be.
I don't know. Is there like some moderator which can unmute you?
Thanks, moderator.
Yes. Yeah.
Nils.
So you should be able to speak now.
Okay, now,
Yeah.
now I think you are unmuted.
Yes. Hi, Nils, can you hear me, right? Nils, you can hear me, right?
Yes, we can hear you.
I can hear you. Yes.
Yeah. So, my question here, so we are talking about semantic search, and for example, if we given a query and we are able to extract the closest sentence to the given query, right? So my question here, let's say in the example, my query here, can I have your mobile number, and I'm having some sentence, I need your mobile number for reference. Okay, so if you do the semantic, calculate the distance, it will be like it's very close. Okay, so my intention here, okay, since it is close, okay, but I need to extract only sub part of the sentence, because I don't if you ask me, right, in the sentence, I need your mobile number is exactly matched to the can I have your mobile number, right? Maybe I can give another example. Maybe in my sentence I have some lot of.
I cannot hear you, or I cannot hear you.
Oh, sorry. Is anybody? Okay, so while you're calculating semantic search, right, for the sentences, okay, so we calculate for the entire sentence, Nils, right? Okay, so just I want to extract.
Can you start over? The audio was muted for me for Discord.
Can you hear him now?
Now I can hear him. Just notice that
okay.
The audio was muted for me for Discord.
Okay.
Do you want me to repeat the question, Nils?
Please, so I was not able to hear you.
Okay, you able to hear me now, correct?
Now I can hear you.
Yes.
So let's say the query and the sentence, if you calculate the similarity between the query and sentence, it will be very close because of the mobile number and the context, correct? Let's say if the sentence something like this, my name is Yashwant and I want to talk with you and I need your mobile number for reference. So this is a huge sentence compared to the sentence I given here. So my intention is from the sentence, I need to extract only sub part of sentence which is very close to the query like given there.
Mm-hmm.
You are getting my point, right? So I don't want my name and the greeting and all. I just my interest is to I need your mobile number which is exactly close to my query. You are getting my point, right?
Yeah. So there's an approach called reader. So this is like really old approach, which was like also included in the BERT paper. You concatenate the query and the document. Then you do predictions for all the spans, like should this be extracted? So you have the query and then you have the document, and then you train the model so that it just extracts, I need your mobile number. You wouldn't need to have some training data. So people do it for like Q&A. Say, okay, this is a question, and then where in this paragraph exactly is the answer? Is it like a word, a phrase, whatever? If you have training data for this, then you can do it like this. If you do not have training data and you do it with embedding approaches, people use like a sliding window. So you take a window, you slide it over the answer text, and then you'll see, okay, which window is the highest, and then you would have like, I need your mobile number, has the highest similarity to can I have your mobile number.
Thanks for answering. I would just like to ask people if anyone else has any more questions, and you can ask them in the chat. And if no one has anything else to ask, I would like to thank you so much for this interesting talk and for answering our questions. And yes, thank you so much. It was really interesting, and I would just like to say that we have other events coming next month, so you can check them out. So yeah, thank you so much for coming, and thanks everybody for listening and asking questions.
Thank you for organizing the Discord.
Thank you.
Bye.